Now we come to chapter 6, module 5. In this module, we shall see how Fourier transform can be applied to solve linear ordinary differential equations. We shall consider here some examples. We consider first example. Consider the linear ordinary differential equation, in short we call it as ODE, d square f dx square plus a df dx plus minus b f equal to gx, where the range of x is from minus infinity to plus infinity, with the condition fx and f dash x both tends to 0 as x tends to plus minus infinity. Also here a and b are constants and gx is a given function which is known, whose Fourier transform also exists. Now we shall apply Fourier transform to solve this linear ordinary differential equation. Let capital Fs denotes the Fourier transform of small fx, which is given by 1 by root 2 pi integral minus infinity to plus infinity small fx e to the power I sx dx, and capital Gs is the Fourier transform of the given function small gx, which is given by 1 by root over 2 pi integral minus infinity to plus infinity gx e to the power I sx dx. Now we will apply Fourier transform to the given differential equation. Before that, we calculate the integral minus infinity to plus infinity d2f dx2 e to the power I sx dx and integrate this by parts. So the first term is f dash x e to the power I sx, x ranges from minus infinity to plus infinity, minus is integral from minus infinity to plus infinity f dash x e to the power I sx dx. Now from the given condition of the differential equation, fx and f dash x both tends to 0 as x tends to plus minus infinity. So here the first term vanishes and we obtain 0 minus is integral from minus infinity to plus infinity f dash x e to the power I sx dx. Now this integral we again integrate by parts, so that we obtain 0 for this term minus is fx e to the power I sx minus infinity to plus infinity minus is integral minus infinity to plus infinity fx e to the power I sx dx. Again from the condition of the differential equation, we have seen that fx also tends to 0 as mod x tends to infinity. So this gives the first term here as 0 and we finally get minus s square capital F s, where capital F s is the Fourier transform of small fx. So this integral is evaluated as minus s square capital Fs. Next we evaluate integral minus infinity to plus infinity df dx e to the power I sx dx. Again we integrate this integral by parts and use the condition f tends to 0 as mod x tends to infinity to obtain this integral as minus is into capital Fs. So with this result we multiply both sides of the given ordinary differential equation by e to the power isx by root over 2 pi and integrate between minus infinity to plus infinity with respect to x. And using these results we find the ordinary differential equation reduces to minus s square plus ias plus b into capital Fs, that is equal to capital Gs. So that capital Fs is equal to minus capital Gs divided by s square plus ias plus b. Now, if we take the inverse of capital Fs from here, whole thing, if we take Fourier inverse, then we find small fx, which was the required function which is to be found out, which is the solution of this differential equation. So, next task is to find the inverse Fourier transform of this expression. Now, to find the inverse, we note that this function, that means 1 by s square plus ias plus b, this can be rewritten as 1 by s plus I a by 2 whole square plus s square by 4 plus b. Now, we are to find Fourier inverse of this function. To find Fourier inverse of this function, we shall first find the Fourier inversion of the function 1 by s square plus c square, where c is a constant which is positive. Now, Fourier inverse of 1 by s square plus c square according to formula of Fourier inverse, this is given by 1 by root 2 pi integral minus infinity to plus infinity e to the power minus I s x divided by s square plus c square ds. Now, we are to evaluate the integral on the right hand side. To evaluate this integral, we use the complex variable theory. First, we choose x as positive. Now, to evaluate this integral, we consider the contour as given in this figure, that is figure 1, that is from r to minus r, capital R, and an arc of a circle which is denoted by gamma dash r. This is the contour. Here capital R is a very large positive number and gamma dash r, as we see that it is a half circle in the lower complex half plane with radius capital R and center as origin. So, this is the contour. Inside this contour, we see that this function has got a pole at s equal to minus IC. So, using the residue theorem of complex variable theory, we can write this integral as over this contour as from my r to minus r on this line plus on gamma r, that is on this arc of the circle, which gives the left hand side, and that is equal to twice pi I into residue at x equal to minus IC, that means at this point, at this pole. Now, on the arc gamma r dash, the integral, this integral this tends to 0 as capital R tends to infinity by Jordan's lemma of complex variable theory, and the residue at x equal to minus IC can be calculated as limit x tending to minus IC x plus IC into e to the power minus I x s divided by s square plus c square, and that comes out to be e to the power minus Cx divided by minus 2 IC, thus making capital R tend to infinity. Here in this integral we find that this part on this integral is 0, and we make capital R tend to infinity, and we have calculated the residue to obtain for x positive integral minus infinity to plus infinity e to the power minus I x c divided by s square plus c square ds, that is equal to minus 2 pi I e to the power minus c x divided by minus 2 I c, which can be calculated as pi by c e to the power minus c x. Next we consider when x is negative. So, when x is negative, this integral minus infinity to plus infinity e to the power I minus x s divided by s square plus c square can be evaluated by considering the figure 2, that is the contour given in figure 2. So, when x is negative, minus x is positive. So, in the complex S plane, we consider this half circle, that is contour consists of line from minus r to plus r and an arc of half circle which is given by gamma r. So, inside this contour we see that the integrand e to the power minus I s x divided by s square plus c square has a simple pole at s equal to plus I c. So, by using complex variable theory, the integral, this integral can be written as integral from minus r to plus r plus integral over gamma r of e to the power minus I x s divided by s square plus c square ds, which is given as 2 pi I into residue at x equal to IC. Now, using Jordan's lemma, it can be seen that the integral over gamma r, that is this integral, tends to 0 as mod r tends to infinity, and the residue at x equal to IC is limit s tends to IC s minus IC into e to the power minus I s x divided by s square plus c square, and this is equal to e to the power c x divided by twice I s, and which can be written as e to the power minus c into minus x divided by twice I c. Thus, making capital R tend to 0, we find for x negative the integral from minus infinity to plus infinity e to the power minus I s x divided by s square plus c square ds, this is equal to pi by c e to the power minus c into minus x. Hence, for x positive and x negative, this result can be combined to write integral from minus infinity to plus infinity e to the power I s x divided by s square plus c square ds, this is equal to pi by c e to the power minus c mod x. So that Fourier inverse of the function 1 by s square plus c square will be given as, if I multiply 1 by root 2 pi both sides, then Fourier inverse of 1 by s square plus c square is equal to root over pi by 2 e to the power minus c mod x divided by c. Now, suppose capital Ls is the Fourier transform of small Lx, then we can write capital Ls is equal to curl f of small Lx. Now, from shifting property of Fourier transform which we have learnt earlier, we know that Fourier transform of the function e to the power I a x into Lx, that will give as capital L of s plus a. So that Fourier inverse of capital L s plus a, that is equal to small Lx e to the power I a x. Now, we choose capital L s equal to 1 by c square plus s square. So that small Lx will be equal to root over pi by 2 e to the power minus c mod x divided by c. Hence, capital L s plus alpha is equal to 1 by s plus alpha whole square plus c square. So that by shift property, Fourier inverse of 1 by s plus alpha square plus c square, that will be equal to e to the power I alpha x into root over pi by 2 e to the power minus c mod x by c. So, we use this to find Fourier inverse of 1 by s square plus I a s plus b, that will be equal to Fourier inverse of 1 by s plus I a by 2 whole square plus a square by 4 plus b. Now, we choose alpha equal to I a by 2 and c square equal to a square plus 4b by 4. So, Fourier inverse of 1 by s square plus I a s plus b is given by root over 2 pi e to the power minus half into a x plus root over a square plus 4b mod x divided by root over a square plus 4b, and that we write as root over 2 pi into nx. So, that nx is the function e to the power minus half into a x plus root over a square plus 4b into mod x divided by a square plus 4b. So, the solution small fx of the ordinary differential equation which is given can be found out as minus Fourier inverse of g capital G s into 1 by s square plus I a s plus b. Now, capital G s, as we know that it is the Fourier transform of small g x, and 1 by s square plus I a s plus b is Fourier inverse we have found out just now. So, Fourier inverse of the function on the right hand side, that means this function, this is the product of Fourier transforms of two functions. So, that we can, its Fourier inverse we can write it as the convolution of the function gu and root over 2 pi n x, and that is given by minus 1 by root over 2 pi minus infinity to plus infinity integral gu root over 2 pi n of x minus u du. This is by convolution theorem, and which is found to be equal to minus integral minus infinity to plus infinity g u n x minus u du, where nx is given above. So, this is how we have found out the solution of the given differential equation. Now, we consider the special case of the differential equation where a equal to 0, b equal to 1 and the function on the right hand side g x equal to minus 1 for minus 1 less than x less than plus 1 and 0 otherwise. So, that means the given differential equation reduces to an ODE d2f dx2 minus f, that is equal to minus 1 when x lies in the interval minus 1 to plus 1 and 0 otherwise, with the condition small f and f dash tends to 0 as mod x tends to infinity. So, we have found from the previous analysis that nx, this will be equal to half e to the power minus mod x by considering a equal to 0, b equal to 1. Hence, the solution f x is given as half of minus 1 to plus 1 integral e to the power minus mod x minus u du. Now, substituting x minus u as t, this integral is written as half integral from x minus 1 to x plus 1 e to the power minus mod t dt. Now, for mod x less than 1, we shall evaluate this integral by breaking this integral from x minus 1 to 0 where t is negative. So, that the integrand here e to the power minus mod t becomes e to the power t dt, and in the second integral, that is from 0 to x plus 1, the t function is positive. So, that this integrand becomes e to the power minus t dt. So, that this integral can be evaluated as 1 minus 1 by e cos hyperbolic x for mod x less than 1. Also, considering the same way, f x is equal to half of integral minus x minus 1 to x plus 1 e to the power minus t dt for x greater than 1, and this comes out to be e to the power minus x sin hyperbolic 1, and for x less than minus 1, the integral half x minus 1 to x plus 1 e to the power t dt, which is equal to f x, that comes out to be e to the power x sin hyperbolic 1 for x less than minus 1. So, we have found out for mod x less than 1, the solution f x is given by this function, and for x mod x greater than 1, the solution of the given differential equation in the special case is given by f x here. So, in this example, we have seen that how Fourier transform can be applied to solve an ordinary differential equation. Also, in this example, we have seen how complex variable theory can be applied to find the Fourier inversion of a function. Next, we consider another example. Example 2, use Fourier transform to solve the differential equation d2f dx2 minus f equal to e to the power minus mod x, x ranges between minus infinity to plus infinity, with the condition f and f dash tends to 0 as mod x tends to infinity. We are to solve this differential equation using Fourier transform. So, taking Fourier transform on both sides of this differential equation, that is multiplying both sides by 1 by root over 2 pi and integrating from minus infinity to plus infinity with respect to x and e to the power I s x, we find that this reduces to minus s square capital F s minus F s equal to root over 2 by pi 1 by s square plus 1, which can be simplified to be capital F s equal to minus root over 2 by pi 1 by s square plus 1 whole square. Here capital F s is the Fourier transform of small f x. Now we rewrite the expression for capital F s in certain fashion. Now from this expression for capital F s, if we can find out the inverse of this function on the right hand side, then we will get the solution small f x of the given differential equation. So, small f x will be given by 1 by root over pi by 2 Fourier inverse of root over 2 by pi 1 by s square plus 1 into root over 2 by pi 1 by s square plus 1. This expression is just an arrangement of the expression on the right hand side here. So that f x can be written as minus root over pi by 2 into 1 by root over 2 pi integral minus infinity to plus infinity e to the power minus mod u into e to the power minus mod x minus u du. Now the inverse transform of this function gives this, and this step is obtained by using the convolution theorem for Fourier transform. So that we obtain f x as minus half integral minus infinity to plus infinity e to the power minus mod u minus mod x minus u du. Now we break this integral into minus infinity to 0 and 0 to infinity. So that we obtain f x as minus half integral minus infinity to 0. In minus infinity to 0 integral u is negative. So that e to the power minus mod u will be e to the power u. So that we get minus half integral minus infinity to 0 e to the power u minus mod x minus u du plus integral 0 to infinity e to the power minus u minus mod x minus u du, because in the range 0 to infinity for u e to the power minus mod u is e to the power minus u. Now we have to consider this expression. So this step can be further simplified as minus half integral 0 to infinity e to the power minus u minus mod x plus u du plus 0 to infinity integral e to the power minus u minus mod x minus u du. The first integral here is obtained by changing the first integral here into 0 to infinity. So that we obtain this small f x as equal to minus half integral 0 to infinity e to the power minus u into e to the power minus mod x plus u plus e to the power minus mod x minus u du. Now, let small L1 x is equal to integral from 0 to infinity to the power minus u minus mod x plus u du, and L2 x is equal to 0 to infinity integral e to the power minus u minus mod x minus u du. That means, the first term, that is the first integral, we call it as L1 x, and the second integral we call it as L2 x. Now, for x positive, this L1 x can be written as integral from 0 to infinity e to the power minus u minus x plus u du, and that can be evaluated as half into e to the power minus x. Now, for x positive, the integral in L to x, that means here the range of integration has to be divided into two integrals. That means, L2 x is equal to 0 to x e to the power minus u minus x minus u du plus integral from x to infinity to the power minus u minus x du. In the first integral, here u is less than x, and in the second integral u is greater than x. So, that this mod x minus u is written accordingly, and considering this, L2 can be evaluated as half of e to the power minus x plus x e to the power minus x. So, that we write f x, small f x, that is the solution of the given differential equation, as small f x equal to minus half x plus 1 into e to the power minus x for x positive. Now, for x negative, we write x equal to minus x dash, that means x dash is positive. So, in this case, L1 x will be equal to L2 x dash. L1 x is given by this integral. If we substitute x equal to minus x dash, then we obtain L1 x equal to L2 x dash, and which can be evaluated as half of e to the power x minus x e to the power ex. And L2 x, by substituting x equal to x dash, this becomes L1 x dash, and that is evaluated as half into e to the power x. So, in this case, f x is given as minus half 1 minus x e to the power x for x negative. So, combining these two results, we find for this is for x negative and this is for x positive. So, combining these two results, we find the solution of the given differential equation f x is equal to minus half into 1 minus mod x into e to the power minus mod x. So, this is the solution of the given differential equation. So, in this module, we have seen how Fourier transform can be applied to solve linear ordinary differential equation. With this, we conclude this module.